Hello everyone, my name is Dr. KCH Apparao, working as an associate professor in Mechanical Engineering Department. Today I would like to explain about the tool life. So this one is the course outcome. At the end of the course, students should be able to coolants and tool materials for the analysis of material behavior during the manufacturing process. We'll see first. So tool life is mainly depend upon the tool wear. So first of all, we'll see what is tool wear. Wear rate or tool wear is a term that describes the gradual failure of a cutting tool due to its operation. A cutting tool is ground with various angles to perform the cutting operation efficiently and effectively on different materials in different situations of various speed, depth, and the field of cut. Okay. So under a regular operation, the tool wears out gradually, leading to changes in the angles ground on the cutting tool. So which in turn ends the tool to function satisfactorily. So a very short tool life is not economical because as tool grinding or tool replacement increases the cost of machining, in turn increases the cost of the product. Okay. So tool wear cannot be avoided, but we can reduce the tool wear by suitable operational conditions or operating conditions. Okay, we'll see what are the different operating conditions which will help to reduce the tool wear. So first of all, we will see what are the different conditions which affect the tool wear. The first one is the high localized stresses at the tip of the tool. Next to high temperature, it is very important parameter, especially along the rake face and sliding of this chip along the rake face. Okay. Next to sliding of the tool along the newly cut workpiece surface. Okay. So these conditions induce the tool wear. So which is the major consideration in all machining operations. Okay, tool wear adversely affect the tool life because tool life is mainly depend upon the tool wear. The quality of the machined surface, because tool wear adversely affect the tool life. Next to quality of the machined surface and its dimensional accuracy and the economics of the cutting operation also, because tool life is very important parameter. We have to study about this one because the tool uh, life is depend upon the tool wear. We should know about the tool wear, what is what are the different parameters which are affecting the tool wear also. So this one, the graph between the tool wear and time of cutting also. So here this shows the rapid initial wear. So here from this place to this place, that is the steady state wear region, uniform wear rate we can observe here. So next one, this is the failure region, just to time of cutting is more. This one is the final. So here the wear rate accelerated, so increases rapidly. Okay, here. So this one is the wear rate. Now we'll see tool life. What is the importance of the tool life? How this wear rate influences the tool life? Okay. So tool life is the time duration. A tool can be reliably used for the cutting before must be reground or discarded. So it is the uh, duration of time for which it was intended to use. So the life of the cutting tool is one of the most important to economical consideration in metal cutting, because tool life or cutting tool is very the life of the cutting tool is very important. So tool must be utilized efficiently to the maximum possible extent before it can be ground or discarded. Okay? Because tool grinding or replacement costs are very high. So the life of the tool is affected by various parameters. We'll see what are the different parameters. We'll see first of all what is tool life and what is the definition of the tool life also. As the machining operation progresses, the cutting edge of the tool gradually wears out, and at a certain stage, it stops cutting metal efficiently as per the requirement. Okay, so it has to be resharpened to make it cut. Okay, so useful cutting life of the tool from the start of cut to until such a time when the tool no longer performs the design function defined by the failure criteria. Okay. So that is the life of the tool or time of the tool. Okay. So tool life is defined as the length of the cutting time that the tool can be used satisfactorily. So this is the definition of tool life. So tool life, the time from the start of cut to some endpoint defined by the failure criterion. Okay, so this is the nothing but tool life. We'll see what are the various possible indicators of the end of the tool. So by observing these indicators, you can understand the uh, life of the tool or end of the tool life. Okay. The first one is the failure of tool. Okay. So we observe rough machining. Next to extent of tool wear. So tool wear increases rapidly, and poor surface finish. Okay. So we get a very rough or poor surface finish. Dimensional instability also we can observe. So that shows the tool should be uh, changed. Okay. Next, sudden increase in cutting forces and power also. So there is a fluctuations in cutting forces and power. Next, overheating and fuming also we can observe. Okay, when machining perform the machining operations. Next, presence of chatter also we can observe. So these are the indicators to identify the end of the tool life. Okay. So now we see. So these are the factors which are influencing the tool life. So we have to study about these points carefully. The first one is the cutting speed. It's very important parameter. So it is represented by V. You know this one. Next, feed and depth of cut. So F and depth of cut D. These parameters also very influential parameters for the tool life. Next, tool geometry, mainly uh, rake angle. Okay. So next, tool material also influences the tool life, because different materials can be used for the machining based upon the design of product. Okay. Next, to cutting fluid. Cutting fluid is very important to reduce the frictional heat. Uh, so which one develops between the tool and the workpiece. Next, to work material also. Tool material and work material both are very important. So next, to rigidity or fixing of the workpiece, tool and machine. So these parameters also very important. If there are any fluctuations or any next to shakings, that leads to just increasing the life of the wear of the tool. Okay, so these are the very influence parameters which are affecting the tool life. Okay, we'll see first of all the cutting speed. So this is very important to parameter. The cutting speed increases, the cutting temperature increases. Okay, So the greater the temperature influences the cutting tool life, because if the temperature increases, automatically the hardness of the tool life decreases because of the temperature. So the hardness of the tool decreases, automatically tool flank wears and crater wears occurs easily because of sharpness. So because the hardness increases, if the temperature of the tool increases, automatically the hardness of the tool will be decreased. So that leads to flank wear and the crater wear occurs easily. So due to these reasons, tool life also decreases. Okay. So the relationship between the tool life and the cutting speed is expressed by Tyler. So Tyler has given one formula to understand the relation between the velocity or speed of the cutting speed and life of the tool. Okay. So T shows the uh, tool life and V is the cutting speed. So according to his Tyler's, the formula is V to the power of n is equal to C. Okay, so n shows the just like exponent. It is depend upon the tool and workpiece materials. Okay, so tool material and workpiece material. You can see for the HS high speed steel making for the tool, and workpiece material is in MS mild steel. Then you can take n is equal to 0.1. So there are different n values based upon the tool material and workpiece materials. Okay, so this is the formula you can see here. According to Toilers, he has given some equations. These are the tool lives. He has taken T1 at velocity V1, T2 at velocity V2, and T3 at velocity V3. Okay. So T4 at velocity V4. Okay. If the velocity increases, tool life decreases. If velocity decreases, tool life increases. So this curve shows here just like hyperbola, just like rectangular hyperbola. It appears like this one. So the Euler floated the same figure by taking the logarithms log of v. So this is the cutting velocity. This is the tool life. Then he applied the log v and log t. Automatically, this curve appears as a just like linear relationship. This shows the linear relationship. The angle of this one are same. Okay, so that is the tan alpha is equal to n parameters. Okay, based upon this one, he has given the formula, that is the with the slope and n and intercepts constant c. He has given the formula Vt to the power of n is equal to c. Okay. N is called the Euler's tool life exponent, and the values of n and c are depend upon the tool material and workpiece material. Okay. And the cutting environments also. Okay. Here, suppose initial condition velocity cutting speed is equal to v1 and time of the tool life is equal to t1. For the second condition, if you take velocity tool speed cutting speed is equal to v2 and time is equal to t2. So then the relationship between these two is equal to v1 t1 to the power of n is equal to v2 t to the power of t2 to the power of n. Okay, so we can write like this one: v1 by v2 is equal to t2 by t1 t1 to the power of n. If you apply the logarithmics automatically, then we'll get this one like this. So log of ln of v1 by vt is equal to n into ln of t2 by t1. Okay, like this one. So taking the log on both sides, ln v1 by vt is equal to n log of t2 by t1. Then n is equal to ln v1 by v2 by ln t2 by t1. Okay, so this is the formula. By using this parameter, we can find out the exponent of Euler's tool life. So we'll see. These are the values of n for the different tool materials. For the HSS, the value of n is equal to, it varies between the 0.1 to 0.18. Next, the tool material is tungsten carbide, WC. The value of n exponent value is equal to, so in between 0.2 to 0.25. So next, the tool material is coated WC, tungsten carbide tools. So you can take n is equal to 0.3. If you tool material is coated with the aluminum oxide, just Al2O3, then n will be taken as 0.4. If you take tool materials as ceramic tools, okay, then n value varies between 0.4 to 0.7. So we can take the value of n based upon the tool material. Okay. Here, uh, here one more Euler's tool life equation you can see. This one is the modified tool life equation, because in the previous one we saw only the relationship between the speed, cutting speed and time, tool life. Okay, so v t to the power of n is equal to c. So this is the formula. Here just two more parameters are included here, so which are influencing the tool life. That one is the field. That parameter also very important. Next, depth of cut, d. So these two parameters are very important, which are influencing the tool life. Okay, so including these, the formula has been given by Euler's is like this one. So that is the v t to the power of n, f to the power of x, d to the power of y. So n comma x comma y. So these are the just exponents. So these exponent values is depend upon the work material and tool material and machining environment also. Okay. So this is the relationship. So generally y comma x, just generally x greater than y greater than n. Okay. So that affects the tool life maximum. Okay, d minimum. So we can observe this one. Next, so which are the some parameters which are influencing the tool life also we'll see. So the first one is the rake angle or rake face. So these are very important parameters which are influencing the tool life. So the first one is the back rake angle. Generally when the back rake angle increases, it means back rake angle means positive rake angle increases, cutting force decreases. So that automatically that improves the tool life. Okay. So if too large makes edge fragile, so we can consider that point also. So suppose when the back rake angle are negative, so the back rake angle increases or back rake angle decreases, means if the back rake angle is negative, the cutting force, we have to give the more cutting forces. The cutting forces are larger. So subsequently, automatically, so tool life is reduced. Okay, for the positive rake angle, tool life increases. For the negative rake angle, tool life decreases. Next to side rake angle, larger side rake angle produces chipping on cutting edges. Smaller side rake angle generates the greater heat. Okay. So greater heat or excessive wear and deformation tools. So small side rake angle that leads to automatically greater heat. So that heat reduces the hardness of uh, tool material, that leads to wear, increase in wear rate. Okay, so we have to consider those things also. So next one, clearance angle. This one also very important. So inadequate clearance angle reduces the tool life and the surface finish also. Okay, so here we can see here a particular point, up to particular point tool life is minimum. Next to in previous and ending, the tool life is decreases. So too large clearance reduces the tool strength and tool life is decreases. So we have to understand the optimized clearance angle, then we can increase the tool life also. So next, feed and depth of cut. Okay, so tool life is depend upon the amount of material removed by the tool per minute. Okay, so for a given cutting speed, if the feed or depth of cut is increased, the rate of material removed so will reduce the tool life. Okay, next, tool geometry. This one also very important parameter which influences the tool life. Large rake angle, already we covered this one. Large rake angle reduces the tool cross section, so area of tool which will absorb heat is reduced. Okay, if the cutting angle increases, more power will be required. So the if you give the more power, automatically the tool life will be decreased. Next, clearance angle will improve the tool life at first, then tool life decreases because the decrease in the strength. Okay, these points already covered in previous slides. Okay, next to tool material. So tool life also depend upon the tool material, because we know the formula V2 for N is equal to C. So N is depend upon the tool material. Okay. So tool material, tool life is depend upon the tool material HSS. Okay. Next, to cutting fluid, very important parameter. So cutting fluid reduces the heat which was developed between the tool and workpiece. Application of correct cutting fluid decreases the tool. Okay, next, workpiece material. Workpiece material, physical and chemical properties of the workpiece affect the tool life. So tool life will be more when the machining soft material than hard material like cast iron and bronze. Okay, rigidity of the work and tool and machine also very influence the parameters. Okay, here we'll see one numerical which is based upon the tool life, and we then I would like to stop this lecture. Okay, a batch 500 jobs of diameter 50 mm and the length is equal to 100 mm. So is to be turned at 200 revolutions per minute, and feed is equal to 0.2 mm per revolution. So applying Taylor's equation. So this is the formula. We know this one. VT2 for Fn is equal to. So we have to determine the tool life, so in minutes, and number of components per tool life. So here the given parameters is equal to number of just like jobs, that is n is equal to 500, and the diameter, uh, so diameter of the workpiece, that is the 50 mm, and the length of the that one is equal to 100 mm. Okay, so next to n is equal to speed is equal to 200 rpm, and feed also given 0.2 mm per revolution. So we know that the formula also given Vt to the power of n value 0.25, that is equal to 160. It has given one relationship also. So this is the okay. So next to T is the just a 674 minutes to life is more than the machine tool. Okay. So this one is the, we have to solve this one first. First you have to find out the, so n has been given, then we have to find out the speed. Speed is equal to V is equal to pi d n by 60. You know this one. Okay, so pi value and d is the diameter, n is the speed, n value by, so this is the in mm means, so we can take this is 1000. Okay, then if you solve this one, velocity, cutting speed is equal to 31.4 mm per minute. Okay, so here we know this v. If you substitute the value of v here, then you can find out the t value. So the t value is equal to 674 minutes. Tool life is more than the machine tool. So next, the number of parts produced is equal to tool life by t mean. T mean is equal to, we have to find out this T mean also. This is the formula for the T mean. So machining time per one part, so that is equal to total length by F into N. F is the feed, N is the speed, and L is the length. 100 by 0.2 into 200 is equal to 2.5. So if you substitute this value Tm here, then you can find out the value, that is the 270. 270 parts can be produced in the particular tool life. So that is the 674 minutes tool life. So this is a numerical which is based upon the Toller's equation for the finding of tool life. Okay. So thank you for listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.